Hello, my name is Samuel Jung, and I'll be presenting my research on complex time stepping in numerical methods. This research was done in collaboration with Jitin George and my faculty advisor, Neil Mangan. So a numerical method is something that is used to approximate a differential equation. This is done because there are many instances where differential equations are way too hard to solve or take way too much work and are just really a pain to deal with. So because of that, we have these numerical methods that in turn approximates what the solution to the differential equation should be, foregoing some accuracy, but we have an approximation that can be really good. So the first kind of numerical method is called the forward Euler method. So what a differential equation tells us is the slope or the derivative of a function at any given time. So you can exploit that because you know the function should change with that derivative in time. So if you multiply by some delta t, then you have an approximation of what the value of the solution should be at that time point. And so you see that the two dots aren't exactly the same. They're pretty far apart actually, but we still have an approximation and that's where we're starting from. So what we're solving today is the linear ODE, y prime equals y, and it has this solution where y of delta t is equal to e to the power of delta t. So the nice thing about this is that you could Taylor expand e to the power of delta t and have an exact solution at the polynomial that goes out to infinity. And so if you look at your forward Euler scheme and look at how it's written, what you actually see is that the first two terms of the Taylor expansion in the forward Euler scheme, 1 plus delta t, they match up exactly. And so you call this forward Euler scheme first order accurate because it matches delta t up to the first order, first power. So naturally, the hope is that you can get even higher orders of accuracy. You can have delta t squared, delta t cubed. So that's where complex time steps come in. So the thing is, you can't actually reach this delta t squared value without taking a complex value time step, is what we have found. And not only that, but if you want delta t squared time, then you need to take two steps. So what you actually find is that the nth order of accuracy corresponds to an n number of steps as well. So if we actually look at the complex second order scheme, we have two complex valued steps that we're taking in time. And then if we expand it out, what we actually get is we get up to 1/2 delta t squared. And that shows us that we have our second degree accuracy, our second order of accuracy. And then same thing with third scheme is we find this scheme right here, and then we have third order accuracy. So the way we've done this is we have an optimization routine that we run ourselves. It's way too much to show in this presentation, but that's how we got these values. And so these steps in complex time might not really make any sense because they really don't. But if we look at the visualization of what's going on here, if you imagine the forward Euler scheme, it's actually just going from 0, 1, 2, 3, linear time, and everything's fine. But if you look at the complex second order, you actually take the zigzagging path. You hit all the same real time points, but you go zigzag. And then third order, you're doing this trapezoid thing, and you still hit all the real time points. So you evaluate to the same points, but you go through the complex plane to achieve it, and you take 2 steps, 3 steps, whatever, n number of steps. You can do how many you want. So now that we have this, and now that we've gotten our schemes, we want to make sure that the theoretical accuracy that we're stating is matched experimentally. So that means if we actually run this scheme on our linear ODE, then we should get second degree accuracy. So that's why we have this log-log convergence plot right here. And this shows us that that's actually true. So what these lines are is how the error should scale with the size of your time step if it was truly scaling with delta t. And same thing with delta t squared and delta t cubed. And if you actually plot the values for each one, you find that it actually does match up. And so this confirms that experimentally that our theoretical order of accuracy is true. And so this below graph just highlights that for us. So the third order seems to be tracking just right on top of the analytic solution, which is way big of an improvement compared to forward order, which is all the way down here. Keep in mind, this is a 1e to the 10 scale on the y-axis. So that's really bad for forward order at time 25. And our complex third order is doing pretty well. So conclusions of this is the first time an analysis has been done for complex time stepping like this. It's really easy to implement, and it provides a pretty simple way to get arbitrarily higher order accuracy, and we hope to apply this to nonlinear systems. Thank you so much for listening to our presentation. I hope you have a nice day.